Numbers have always fascinated humanity. From the simplest counting to the deepest mysteries of prime numbers, mathematics has been the key to understanding patterns in our universe. But what if there was a deeper layer to numbers, an unseen structure that connects primes, twin primes, composites, and even Gaussian and Mersenne primes in ways we never imagined? Today you will be introduced to a mathematics which I called ultimate mathematics. The reason for this choice of words is that this is mathematics which unveils secret properties of numbers. Now, we're diving deep into the fascinating world of prime numbers and their unique types. The prime numbers and their types which we are going to explain in this video are prime numbers, composites, twin primes, twin prime companions, lonely primes, prime index additive primes, prime index additive composites, same rank composite plus prime equals prime, Mersenne primes, Gaussian primes, factorizing primes in the complex domain, group structure, twin prime companion, or TPC, index positionally additive primes, index, TPC concatenated prime, at the end twin TPC. Today, in this video, we will discuss the first four headings. The mathematics of prime numbers has fascinated mathematicians. Since humans started to count, prime numbers are a class of integers that are only divisible by themselves and 1. Such as, the number 1 itself is not considered a prime number, as some of the prime numbers and their indices are shown as. But there are few questions arises, in which the first query is, whether it is possible to decide if a number is a prime number. Well, there's no easy formula for this. You just have to check if it can be divided by any number other than 1 and itself. Next question. Are there infinite prime numbers? The answer is yes. A long time ago, a Greek mathematician named Euclid proved this answer of the infinity of prime numbers. He used a clever trick called proof by contradiction to show that no matter how many primes you find, there will always be more. Let's see what is this method of contradiction. Imagine we think we've found the biggest prime number. Let's call it p. But can we really be sure it's the biggest? To find out, we multiply all the prime numbers up to p to get a big number, c. For example, c equals 2 multiply with 3 multiply with 5 and so on up to p. Now, let's add 1 with c to get a new number, c plus 1. This new number, c plus 1, can only be one of two things. Either a prime or a composite, meaning it can be broken into smaller primes. If c plus 1 is a prime, then it's clearly bigger than p, proving p wasn't the biggest prime after all. But what if c plus 1 is a composite? Well, it must still be made of prime factors, and since c plus 1 isn't divisible by any primes up to p, its prime factors must be even bigger than p. Either way, we end up finding a prime bigger than p, and this trick works no matter how big p is. This means there's no end to prime numbers, they go on forever. Now the third challenge is, how to find the position of a prime number. When we talk about the index of a prime number, we mean its position in the list of all prime numbers. For example, the index of 2 is 1, the index of 3 is 2, the index of 5 is 3, and so on. But what if we want to know a big prime number, like the 98th prime? We wouldn't know it right away. It's 521, but we'd have to find all the primes up to 521 to be sure. Luckily, there's a helpful trick called the prime number theorem, discovered by Carl Gauss. It gives us an approximate way to find the index of a prime using this formula. I approximately equals p, ln, p. I is the index of the prime, p is the prime number, and ln is the natural logarithm. This formula doesn't give the exact answer, but it's pretty close, especially when dealing with large prime numbers. The bigger the numbers, the closer the formula gets to the truth. But remember, no exact formula exists to match every prime with its index. It's a bit of a mystery, and that's part of what makes prime numbers so fascinating. Now, let us explore another class of numbers known as composites. If we remove all of the prime numbers from the group of integer numbers, then we are left with composites. Composites are numbers that can be factored into primes. For example, 341 is a composite because 341 equals 11 times 31. Euclid also provides proof of the fundamental theorem of arithmetic, which defines as every integer can be written as a product of primes in an essentially unique way. This table shows some composites with their positional indices. Is there an exact relation connecting a composite number to its index? The answer again, just as in the case of primes, is no. This is because composites and primes are connected. If we denote the index of the composite with IC and that of the prime with IP, then the relation would be in the following manner: IC equals P minus IP minus 1. Since we do not know the exact relation between prime numbers and their indices in the above equation, we are unable to establish a one-to-one correspondence between composite numbers and their indices. There is yet another class of prime numbers, differing in magnitude by 2, known as twin primes. Some twin prime pairs are tabulated. Again, the first order of business is to determine if there are infinitely many twin primes. To date, this proof is beyond our capability, although it makes sense that there are infinitely many twin primes. Mathematicians haven't found the proof yet. This makes the handling of twin primes a step more difficult than primes. Is there an approximate relation between twin primes and their indices? The answer is yes, and this relation is due to Hardy and Littlewood. This formula is related to estimating the index I of a twin prime number. The factor 1.32 comes from empirical studies suggesting that twin primes appear less frequently than regular primes. The integral is used to estimate the density of twin primes among numbers. X represents one of the twin prime numbers. ln x is the natural logarithm of x, which helps estimate how primes are distributed. This formula provides an approximation for where twin primes appear. Since no exact formula for twin primes exists, this gives a way to estimate their positions using calculus. Is there an exact relation between twin primes and their indices? The answer is no. Therefore, a one-to-one correspondence between twin primes and their indices is only possible by generating them and tabulating them as in the table. We can list twin primes individually using their index. Let's look at the special composites bracketed by a pair of twin primes. We have coined the name twin prime companion, or TPC, for this class of composites. For example, consider the three numbers 3, 4 and 5, where 3 and 5 are a pair of twin primes and 4 is their companion. Therefore, the first twin prime companion is 4. The indices of these composites are exactly the same as those of the twin prime pairs. The table shows a few twin prime companions with their associated indices. A close inspection of the table reveals that all these numbers, except for the first one, that is 4, are divisible by 6. They all end with 0, 2, and 8 except for the first two, 4 and 6. This specific property of these numbers offers a unique opportunity to generate twin primes without generating the primes first. In our studies of primes, twin primes, TPCs, and their respective indices, we found an approximate relation between twin primes and their indices, which we refer to as the index of the index relation. For example, the 25th twin prime pair is 521 and 523. However, the indices of primes 521 and 523 are 98 and 99, respectively, and there are 25 primes below 98 and 99, which is the index of the twin prime pair, 521, 523. We will continue from here on in next video. Stay tuned and press the like button, and subscribe to our channel and press the notification button to stay updated about the next video.